All right. Well, we'll begin. Today we're covering chapter 3. Which is all about probability. Okay, so let me see if I can pull up an old lecture slide from last week. So last week I said we did this, basics of data collection and data description. This is what we covered in chapter 1. And then today we're going to do probability, and next week we'll do the normal distribution. So normal distribution and sampling, no, just the normal distribution. So this is what we did last week. Today we're going to go over here, and we're going to start learning probability, okay? And it will come together when we do statistical inference, or at least the idea is we build a foundation in probability to get to statistical inference. And so, I mean, when you go through the textbook, it all just feels like we're doing math problems and things like that. But last chapter was about data collection and data description, and then today we're moving into probability, and they'll come together later. Okay, so what are we talking about when we talk about probability? Okay, so what is probability? Okay, so maybe let's just start off with an example. Okay, so we might talk about a coin flip. Okay, so if I flip a coin, I can ask, what is the probability that the coin will land heads? Okay, and so you would tell me that the probability a coin lands heads is 50%, okay, or 0.5. So let me just write that. The probability that a coin will land on heads is 0.5. Okay, so in general, probability we express as proportions. It is completely accurate and acceptable to say 50%, but maybe the norm or the preferred is to say 0.5. But perhaps in class I might even just say 50% interchangeably with 0.5 because they are equivalent. Okay, so also okay to say. Okay, but we say that the probability that a coin will land on heads is 0.5. Okay, and that's assuming we flip a coin, you know, and it's spinning like this or something like that. It's a terrible coin. You know, there's a head over there. Okay, but what does that mean to say that a coin that the probability that a coin lands on heads is 0.5? What exactly do we mean by that? But what does it mean, huh?
Chance.
Okay, we're talking about chance. Okay, well, so we have other words for probability, right? So we've got probability, and we have the word chance and likelihood, and these are all kind of interchangeable. And I could just say, what is the likelihood that the coin will land on heads, or what is the chance that the coin will land on heads? And we're essentially all saying the same thing, right? The probability or the chance that a coin will land on heads is 0.5, or the likelihood that a coin will land on heads is 0.5. But still, what does that mean? If somebody says that the chance that the coin will land heads is 0.5, what do they mean by that? Half the time? Okay. Well, so if we say 0.5, we say, well, maybe we mean, we could say, so one, well, I don't want to write this down. We can say, well, half the time the coin will land heads. But if I flip a coin once, it's either going to land heads or tails. Okay, so you're not going to have half the time of one coin flip. And if I flipped it 10 times, will it necessarily land heads 5 times and tails 5 times? No, I mean, that's certainly possible, but it's certainly also possible for the coin to land heads 4 times and tails 6 times. So, but we all have this notion that the probability that a coin lands heads is 0.5, but what exactly are we talking about here? Okay, yes?
It seems not so much to do with the likelihood, but more the distribution on what's on either side of the coin.
Okay, so based on the properties of a coin, we can say, well, heads and tails should show up with equal chance, and that's how we get to this 0.5 number. But still talking about these things of just, what are, this chance and things. So in this class, we take what we call a classical view of probability, and thus it's going to be a classical view of statistics that maybe in more modern times we have this Bayesian view of statistics and probability and stuff. But here we're going to take the classical, and it's called the frequentist view of probability. And this is how we're going to define probability, which in then turn maybe affects the way we view and understand the interpretations for our statistical inference. Okay, so we're going to just say the classical frequentist view of probability. Okay, and when we talk about probability, we are talking about the long run relative frequency. Long run relative frequency. Okay, so let's get into that a little bit more. Let me just copy this, start a new slide. Let's shrink this a little bit. Okay, so let's say we're talking about a coin flip again. Coin flip of a fair coin. And we define and we say the probability that the coin lands heads is 0.5. Okay? So this is one way to write the statement. The probability that the coin lands heads is 0.5. Sometimes we leave out the R and it's also exactly the same. So these are interchangeable. Okay, so what do we mean by that? So so after one coin flip, perhaps the coin has landed tails. Okay? So what is the relative frequency of heads appearing? Okay? So the relative frequency of heads is going to be, we have seen 0 heads out of one coin flip, so our relative frequency for heads is 0. And let's say for our second flip, let's say we get tails again. Okay? And so what is our relative frequency? I'm just going to write relative frequency of heads. That's going to be, we have seen heads 0 times after 2 flips. Our relative frequency is still 0. Okay? Maybe our third flip is heads, and so now our relative frequency of heads is what? 1 out of 3. So I have 0.33333. Is that okay? And then maybe after the fourth flip is heads, and so that goes into, now I've seen 2 heads out of 4 flips. My relative frequency is 0.5. And let's say the fifth flip is heads again. And so now I have 3 heads out of 5 flips. And so now my relative frequency is 0.6. Okay. Is what I'm doing okay with everyone so far? Okay, and so far our sequence has been tails, tails, heads, 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 okay? And we can just continue this sequence on, okay? So on and so forth. You know, we see more heads, more tails. We just continue flipping the coin repeatedly over and over and over again. And we are going to just keep track of the relative frequency, okay? And so it starts off 0, then it goes to 0.333, then it goes to 0.5, and then it goes to 0.6, and it's going to keep changing. If I bring in, if the sixth flip is tails, then it becomes 3 out of 6, and my relative frequency is back down to 0.5, etc., etc., etc. Okay, we can plot this. Okay, and the textbook shows. The textbook did something. They essentially did this thing, except they have a different sequence. And so if we were to keep track of all of these different things, you know, maybe after one flip it was 0 and whatnot, and as we repeat these things, we can see that these numbers are going to fluctuate and change with every outcome. But in the long run, okay, so after, let's say, millions of coin flips, we expect the relative frequency to be very close to 0.5. Okay, so after a million coin flips, it probably won't be exactly 0.5, but we expect it to be very close. Okay, and the idea is that if we did this an infinite number of times, the value that it approaches, if you've taken calculus, you might be familiar with the concept of a limit. Okay, the value that it approaches, this relative frequency, is the probability of the event. Okay, so after, we can't really say after. So as we approach an infinite number of coin flips, number of trials or coin flips, the value that the relative frequency approaches is the probability of the event. Okay, so that that is what we mean by this classical frequentist view of probability. We're talking about the long run relative frequency, or the value of the relative frequency, the value that the relative frequency approaches as we go towards an infinite number of trials. Okay? Now, this view is perfectly fine and dandy for things like coin flips, where we can easily repeat the action. Things like drawing a card from a deck of cards or rolling a die. These things, we can repeat these very easily, and it's not too bad. But other things in life, we don't have that luxury. Okay, if we talk about, what's the probability that I don't know, the sea level rises 6 feet in the next 20 years, and maybe scientists say that probability is whatever, 45% or whatever it is. Okay, I don't know. If they're talking about these things, we don't have the luxury of having an infinite number of Earths and repeating this thing over and over and over again. But from the frequentist view, we have to pretend that we do have that luxury of having an infinite number of Earths, and it would be as if we could freeze time now, create an infinite number of parallel universes, and see how things play out. And if we say, the probability is 45%, then in about 45% of those parallel universes, this thing would happen, and in the other ones, the event would not happen. Okay, that's the frequentist view. Okay, so I know that's entering the realm of sci-fi with parallel universes, but or some other scientific theories, but that's what we're doing with the frequentist view. Okay, so when we say the probability that a coin lands heads, it would be if we could repeat this an infinite number of times, then we would expect that about 0.5 of those would land heads. Okay, is that all right? Okay, we can. So let me just go through maybe some of the rules. Or here, let's talk about empirical probability. Theoretic probability. Okay. So empirical probability is basically the relative frequency from actual or simulated trials of the event. Okay, so if you wanted to know, so if you flip a coin 10 times and it lands heads 6 times, then the empirical probability of it landing heads is equal to 6 out of 10, or 60%, or 0.6. Okay, so that would be your empirical probability. Theoretic probability, on the other hand, is based on the rules or the axioms of probability. Okay. So we would say, a coin has 2 sides. Each side is equally likely. So the probability that the coin lands heads is equal to 1 out of 2.5. You know what? I think I always forget to fix this. That should improve our color on the screen. Okay, so these are the theoretic probabilities. A coin has two sides. Okay, and the idea is that according to the law of large numbers, as we increase the number of trials, the observed empirical probability will approach the theoretic probability. So perhaps after 10 coin flips, we have only seen probability of it landing heads is 0.6, and the idea is as we increase the number of trials, the empirical probability that we observe will approach the theoretic probability. Okay, and that's basically how casinos stay in business, is because all of the games, the theoretic probability is made in favor of the casino to make money, so that as more and more players play these casino games, the casino will make more money. Okay, I guess not to be confused with gambler's fallacy. Okay, okay, and the gambler's fallacy is that that the universe tries to even things out so it matches the theoretic probability. Okay, the gambler's fallacy is that the universe or whatever forces are at play try to even out observations so they match the theoretic probability. Okay, so according to gambler's fallacy, if you flip a coin 10 times, and let's say you observe 9 heads. Okay, gambler's fallacy might say, well, the theoretic probability is that heads should show up only 0.5, half the time, so therefore in the future tails will need to show up more often to balance this out. Okay, so I'll just write that. So gambler's fallacy, okay, tails will show up more often to balance this out. Okay, but what really happens? Okay, the law of large numbers does state something kind of similar in that as we do more and more trials, this number, the relative frequency, should approach the theoretic probability. Okay, but it's not that tails is going to show up more often to balance this out. Okay, the idea is that as you do more and more trials, those trials will just show up with probability of heads 0.5 and probability tails 0.5, and that if you do it long enough, that whatever appears over there will just overwhelm anything unusual that you see here, okay? So the law of large numbers would be more like, if we do another 1,000 coin flips, we expect something around 500 heads and 500 tails. And so even if you see something unusual like 9 heads in the beginning, after 1,000 more coin flips, it would now only be 509 heads and 500 tails. And so anything, or 501 tails, and so anything unusual that appeared early on just kind of gets drowned out in the among what has happened with the remaining remaining trials. Okay, so the law of large numbers there's no, or LLN, no balancing force, just the true probability or theoretic probability will drown out anything unusual that was observed early on, okay? There's no balancing force, just the theoretic probability should drown out unusual that appeared early on. So that is the law of large numbers. So it is true that as you play more and more, or if you do more and more coin flips, the relative frequency that you observe should approach 0.5. But it's not that there's anything that's trying to balance out anything weird that shows up in the beginning. It's just that the theoretic probabilities will drown out anything odd. Okay, so let's go into some of the rules for determining theoretic probabilities. So actually, so I guess this is all I'm going to talk about: empirical probabilities. Empirical probability is actually very useful when it's difficult to do the math behind theoretic probabilities. Okay, so the rest of today's lecture will focus on calculating theoretic probabilities using these different rules. Okay, but sometimes you've got some scenario or some situation where you don't really know all of the parameters and everything that's going into it. You might have a black box and you're not quite sure what prompts the output. And in those cases, empirical probability is a good way to estimate the theoretic probability. Okay, let's say there's let's say there's just some black box apparatus, and I guess maybe you have the magic 8 ball, okay? And if you don't know what's on the inside of the magic 8 ball, you don't know how often, let's say you want to know what's the probability that the magic 8 ball returns the answer yes, okay? And let's say you don't really know what's going on the inside, okay? On the inside, I think it's a 20-sided die, and so it shows up with probability 1 in 20, okay? But if you didn't know that, you could just spin the 8 ball around and then just repeat this thousands of times and count how often the answer yes appears, okay? And so if you spin it, let's say 1,000 times, then the answer yes should appear about 1 in 20 times, or you should get approximately 50 or so yes answers, and that will give you a general idea of what the true probability is, okay? And so, and that's a silly example, but there's many examples in real life or situations in real life where it might be too complicated to calculate the theoretic probability. And the easiest method is to run simulations or repeat the experiment over and over numerous times to get an idea of what the true theoretic probability is, even if we can't calculate it directly. Okay, and so that's actually the point of many simulations. So people build these computer programs to simulate things, and it's because trying to calculate the probability might be too difficult, but it's actually easier to build a simulation. You know, what's the probability that I don't know, some natural disaster will cause the chain reaction of events impacting this many people. It's too difficult to do the math behind it. It's easier to do simulations, and you don't just do one simulation, you do thousands of these simulations, and then you can get a good idea. Okay, and so presidential elections, a lot of people do things like that. Outcomes of sporting events, they try to run simulations. You know, I guess you could, if you wanted to predict the winner of the Super Bowl or something, there's always like some video game company will always run like Madden and play the video game and see what happens, and they try to make their predictions that way. I mean, that's a silly example, but people do stuff like that all the time for more complicated things. Okay, so anyway, let's go into the rules for calculating theoretic probabilities. Okay, so and we designate events, okay, with letters. So I think in the book they might say E represents an event. And we say, we write that the probability that event E occurs is probability of E, okay? And one rule is that the probability of E is always between 0 and 1 inclusive. Okay. If probability of E is equal to 1, then E always happens, whatever the event is, okay? Always happens, or we might say E is certain. And if probability of E is equal to 0, then E never happens, or E is impossible. All right. We have the complement. Okay, the complement is basically complement of E is when E does not happen. Okay, and we can write, we can say complement of E can be written as E complement, or EC, E prime, but probably I just prefer writing not E. Okay, these are all equivalent ways of writing the same thing. So if we say so just a quick check, if we say we have the event that the coin lands heads, oops, what is the complement of coin lands heads? The complement of the coin landing heads would be the coin does not land heads. Okay? And so that would include every possibility, most of them being the coin lands tails, but anything else, such as the coin disintegrates mid-air because a missile exploded or something, whatever, okay? So everything else other than the coin landing heads would be in the complement of the coin landing heads. Now you could say we're going to just simplify the world so that the only two possible outcomes is the coin lands heads or the coin lands tails, and if one of those two things doesn't happen, then it just doesn't count. And then in that case, the complement of the coin landing heads would be the coin landing tails, because you've said these are the only two possible events. Okay? All right, so we write complement of E as any of these things. So the probability of the complement, so probability of not E, is equal to 1 minus the probability of E. Okay? Notice I'm writing the probability of not E. It is wrong, not correct, to say not E equals 1 minus E, all right? Because E is an event. It's not a number, it's not a quantity. E is an event, okay? But the probability, which is a number between 0 and 1 expressing the probability of that event, is a number, and so we write the probability of not E is equal to 1 minus the probability of E. Is that okay? All right, and let's see. If we have, let's say we have multiple events, okay? Let's say we have events A and events A and B, all right? We can talk about the probability that A or B happens. Okay? And we would write, this would be the probability of A or B. Okay? And the formula for this is the probability of A plus the probability of B minus the probability of A and B. Okay? This is always the case, and so you can imagine we have some space like this. Over here is A, over here is B. Where's my brush palette here?
Is this assuming that A and B are the only options, or
no? No, these are not. So the probability of A happening, okay, is, how do I do this? Yeah, okay. So A can happen, and that's represented by the circle. And if A doesn't happen, that's outside of the circle. Okay? So inside the circle represents A happening. Outside of the circle is A did not happen. inside circle A, it means A happens. Outside circle A means A did not happen. Okay. So with that in mind, what is the total area of this box? What's the probability of the box? 1. Okay? Because inside the circle would be probability of A, and outside the circle would be probability of not A, and we know that probability of not A is equal to 1 minus the probability of A, so if we add those together we get 1. Okay? And then the same applies to B. So let's see. So over here, this is the probability that A happens. And over here would be the probability that B happens, okay? So if I were to add all of these together, probability of A would be what's inside the red circle. Probability of B would be what's inside the blue circle. And if I just added those two together, it would be more than what's covered there. So I have to subtract off the overlap. So there's some overlap here, and that's why we see probability of A plus probability of B minus probability of A and B.
So does this mean that this is the if it's an exclusive OR?
No. It's a anytime you see the word or in probability, it's technically a and or. Okay? It's kind of like in computer science when you say or. So I know in English we have, when we use or, sometimes it means one or the other, okay? And so we might say, do you like vanilla or chocolate ice cream? In probability, your answer is yes. In English, your answer is I prefer vanilla, or I prefer chocolate, or something like that. But in probability, if you like either chocolate or vanilla ice cream, and I ask you, do you like vanilla or chocolate ice cream? Your answer is yes. Or no, if you don't like either form, if you're lactose intolerant and you hate ice cream or something, you know. So when we say or, it's an and or is what we're talking about in probability and statistics. Okay, it's always the case. Is that all right? So probability of A or B is probability of A plus the probability of B minus the overlap, and so A or B is this little shape right here. And so we have a special case. Yes, question.
We've always assumed they're overlapping?
You don't have to, okay? And so actually I'm covering the special case. Special case is no overlap between A and B. Okay, so in this case, our picture looks more like this. Here's A, here's B, okay? And so in this case, the probability of A or B is actually still the same, or we can use the same formula, probability of A plus probability of B minus the probability of A and B. Okay? But what is the probability of A and B?
0.
0. Okay? There's no overlap in this case, meaning if you're in A, you cannot at the same time be in B, and if you're in B, you cannot at the same time be in A. So over here, the probability of A and B is 0, and so it simplifies to the probability of A or B is equal to the probability of A plus the probability of B. So we don't have to worry about the overlap in those cases. We have simple events. Or I should say simple outcomes. Simple outcomes represent situations where each outcome has an equal probability, okay? Each possible outcome has equal probability. So a coin flip is an example of simple outcomes. You have heads and you have tails as possible outcomes, and each outcome has equal probability. Okay, or rolling a fair die. So rolling a die, your outcomes are 1, 2, 3, 4, 5, and 6. And again, all equally likely. Okay. Or picking a card at random. All 52 cards have the same probability of being selected. Okay, and so when you have simple outcomes, and each outcome is also mutually exclusive. Okay, so each outcome is mutually exclusive, meaning there's no overlap between outcomes. Okay, which is actually this situation over here. This is a example of mutually exclusive. A and B, in this last slide, A and B are mutually exclusive. Sometimes the words we use for that are A and B are disjoint. Okay? Meaning there's no overlap. If you're in A, you cannot at the same time be in B. So with simple outcomes, each outcome is mutually exclusive or disjoint. You just take on one of the outcomes and none of the others. And all of the outcomes add up to 1, right? And all outcomes add to 1. So then, in this case, the probability of any event with simple outcomes is equal to the number of simple outcomes included in the event divided by total number of simple outcomes. So for example, let's say we roll a die, and I ask, what is the probability of getting an even number? So in this case, the even numbers are 2, 4, and 6. And then there's 6 outcomes. So the probability of an even number is 3 out of 6, or 0.5. Are you guys familiar enough with a deck of cards? Okay, so if I say we're going to pick a card at random, all right, and I'm going to ask, what is the probability of selecting a face card? Or actually, let's say a black face card. You would say, so face cards are Jack, Queen, and King. The ace is not a face card. There's no face on that card. It's a high value card, but it would not be correct to call it a face card. And then black would be spades and clubs, or clovers, whatever you want to call it. Okay, so the probability of selecting a black face card would then be 6 out of 52, and whatever that simplifies to. I guess I can do the math over here. Just shift setup 2, 6 over 0.11538. Probability of selecting a black face card, 6 out of 52. Okay? Yes, question?
But is that a simple outcome since it doesn't have the equal opportunity? There's less face cards than there are normal cards?
So, picking a card at random from a deck is a situation involving simple outcomes. Okay? So each card has an equal probability of being selected. This compound event, selecting a black face card, in itself is not a I don't know, simple event per se, but it consists of simple outcomes. So the way we calculate it is just counting how many outcomes are included in the event divided by the total number of simple outcomes. Does that make sense? Okay. So let's try another situation. So just this does not work if the events are not simple outcomes. Do you have a question?
Yeah, a lot of times problems about probability are confusing because you can think about it in a different way. Like
Yeah.
you say, we select 6 cards out of 52.
Uh-huh.
You could say we select 1 card and then the next probability of selecting another one
Mhm.
is out of 51.
Yes, yes.
So it really depends how you think about it.
Yes, we will cover those situations in a moment here. Okay, so rules. So I'll try to get to that. And so anyway, okay. So simple outcome rules do not work for situations where outcomes do not have equal probability. So for example, let's say we roll 2 dice. And I ask, what is the probability that the that the sum of the dice is 8? Okay, so the wrong approach, maybe I'll do this in red. Wrong approach would be to say, okay, the possible outcomes for the sum of two dice is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? So these are the possible outcomes when you roll two dice and you add those up. There are 11 possible numbers that you can get. All right? So there's a total of 11 outcomes. It is incorrect to then say sum of 8. Well, 8 is one of these, so it would be wrong to say probability of getting an 8 is 1 out of 11. Okay? 1 out of 11 works if you had 2 through 12 written on slips of paper and you had them in a hat and you were just drawing one of those out. Sure, then in that case 1 out of 11 is correct. The thing going on here is that each of these do not appear with equal probability, right? So if we were to list off the possible outcomes, to get a 2, you can get a 1 and a 1. To get a 3, you can get, I'm going to have to draw better dice here. You can get a 1, 2 and a 1, and a 1 and a 2. Okay? And so on and so forth. And you can look at all the possible combinations. And to get an 8, there are a total of 5 ways. You can get I'm sure there's a picture of this somewhere on the internet that does a better job of what I'm doing here. Let's see. Okay, so there are 5 ways to get an 8. And there's a total of 36 dice combinations. Total of 36 dice combinations. 5 of them add to 8. Okay, and these 36 dice combinations are equally likely. So therefore the probability that the sum of 2 dice is 8 is equal to 5 out of 36.
But that only works if you already know the total combinations. You know that there are 36 dice combinations, but I didn't know that.
Okay, we can talk about, I guess you can list off every single possible dice combination. Okay, and so if you have 2 dice, the first die can go anywhere from 1 through 6, and then the second die can also go anywhere from 1 through 6, and so it creates this multiplication, and you get 36 dice combinations. Okay, and so this actually leads nicely into our next topic of probability trees, which can be useful in calculating maybe some more complicated situations. Okay, so you have to be careful. We can't do this simple outcomes approach and just list off our outcomes this way. We have to think of, well, do we have equally probable outcomes? And if not, then you have to list out the equally, It goes that way. Okay. So let's talk about probability trees as a tool to calculate, probabilities of slightly more complicated events. Okay. So let's just start off with a simple example. Let's say we're going to flip a coin 2 times. And I'm going to just ask the question, what is the probability that after 2 flips, the coin has landed heads at least 1 time? Okay? So we're going to flip the coin 2 times, and we want to know that after 2 coin flips, what's the probability that it has landed heads at least 1 time? Okay, so at least 1 time means it landed heads what? Once or twice, right? Because at least once is 1 or more, and if we're flipping it 2 times, then 1 or more means 1 or 2. Okay, if we flip it 7 times, then it's 1 through 7. Okay, so this means lands heads one or 2 times. Okay, so I'm going to build a probability tree. Okay, I'm going to say this node represents my first coin flip, and there are 2 possible outcomes. Okay, either the coin has landed heads, or the coin landed tails. Okay, and what is the probability of us traveling down this path? 0.5, and the probability of us traveling down this path would be 0.5. Okay, and if you have multiple outcomes or 3 outcomes, then you would have like a third node or third branch coming off, and it's just all the probabilities from all the branches have to add up to 1 at each node. Okay. So if the first coin flip landed heads, what is the probability that the next coin flip, so I'm going to draw 2 nodes from the neck to represent the second coin flip, and it can also go heads or tails. And what's the probability that the next coin flip goes heads? Also 0.5 and 0.5. Okay, and the same applies to this one. We can go heads or tails and I get 0.5 and 0.5 here as well. So if I go down this branch and this branch, then the final outcome, how many times did I see heads? 2 heads. And the probability of that happening is I do 0.5 times 0.5. The probability is equal to 0.25. Here I have seen 1 head. If my first coin flip is heads and the second one is tails, at the end I have seen a total of 1 head, and the probability of that happening here is 0.25. Over here I see tails first and then heads, so I get a total of 1 head as well, and the probability is 0.25. And lastly, I get tails and tails. I have 0 heads, and the probability of that happening is 0.25. Okay. All of these outcomes are disjoint or mutually exclusive. Okay? If I saw heads and then tails, I could not have at the same time seen heads and then heads, or I could not have at the same time seen tails and then heads. So every single sequence is disjoint, okay? So which of these outcomes qualify for the coin has landed heads at least once? Okay? This one qualifies, that one qualifies, and that one qualifies. Okay? So the total probability of us seeing that the coin has landed heads at least once after 2 coin flips would be what? 0.75. I just add these up because they're mutually exclusive, so I don't have to worry about overlap. So the probability of at least one head after 2 flips is equal to 0.75. Is that okay? Another way to have approached this, okay, is we could have said, what are the possible outcomes after 2 flips? I can either see 0, 1, or 2 heads, right? The at least one means I need 1 or 2 heads. And so at least one head is the complement of getting 0 heads. Can you guys see that? So complement means it didn't happen. So if I didn't get 0 heads, I've gotten at least 1 head. Okay? So probability of at least 1 is equal to 1 minus the probability of getting 0 heads. Okay? And in this case it's simple, it doesn't matter, but we could have just found the probability of getting 0 heads, which would have been tails and then tails, 0.5 times 0.5, so I would have done 1 minus 0.25 and gotten 0.75 as well. Is that okay? All right, so this is using a probability tree. Let's just complicate this just a tiny bit more. And we will do an example. Pretty much the same thing. Okay, we're going to flip a coin 2 times. But this time the coin, you know, is bent or weighted or is odd, magical, and has the probability of landing heads equal to 0.7. Okay? And I'm going to ask, what is the probability that after 2 flips the coin has landed heads? Exactly 1 time. Oops. So I will start your tree off here. Okay, and so take a moment here and see if you can answer this question. So I started the tree off. You'll have to fill in the rest of the tree. And this time I'm not saying at least once, but exactly 1 time. Now, I'll just put the answer up here. Well, maybe, well, I don't know. I already did. Okay. The answer's there, and you can just, I'll give you a minute to arrive at this answer yourself, and we can just go over the answer as well. Okay, do you guys also get 0.42? Okay, so if you finish out the tree, you put in 0.7, 0.3, 0.7, and 0.3. Okay, and so the coin has landed heads exactly one time. I'm going to just go ahead and fill in the probabilities here. So here it has landed heads one time, one head. And here also I get one head, right? So it either goes heads then tails or tails then heads. All of the other outcomes don't qualify because this one has 2 heads and this one has 0 heads. So I'm going to do 0.21 plus 0.21 and get 0.42. Okay, so we can now deal with what we call conditional events. Okay. And basically, we are saying the probability of one event depends on the outcome of another event. All right? So, let's say if there is a snowstorm, let's say you're traveling, okay? If there's a, or let's just say if there's snow, the probability that your airplane flight, your flight is delayed is 0.45, okay? And if there is no snow, the probability that the flight is delayed is 0.10, okay? So 45% chance of a delay if there's snow, 10% chance of a delay if there is no snow, okay? And you check the weather. Check the weather report. And they say the probability that there's snow is equal to 30%. I'm going to ask, what is the probability that the flight is delayed? Okay, so in this case, we're going to set up a probability tree as well. Or actually, before I do that, so conditional events, so we write this, we can write these things in a few different ways, okay? So we can just write the probability of snow is equal to 30%, okay? That's just this sentence right here. Is that okay with everyone? All right. But then we say if there is snow, the probability that your flight is delayed is 0.45. This is written this way. We write the probability of a delay, and I'm going to put a vertical bar, which stands for given, or if this thing has happened, and we're going to write if snow. So we say this is equal to 0.45. So the probability of a delay, vertical bar, which is read as given. So we'll say probability of a delay given snow is equal to 0.45. Okay. So then what would I write to get 0.10? I would write probability and then what? Delay, vertical bar, no snow. Exactly. .10. Okay? So this information can also be conveyed with these three equations right here. So I'm going to draw a tree, okay? And we're going to say, okay, well, let's see if there is any snow or no snow. Okay, what is the probability of there being snow? 0.3, which means the probability of no snow would be 0.7, okay? And if there's snow, then two things can happen. There's a delay or no delay. And if there's no snow, two things can happen. There's either a delay or there's no delay. Okay? So what number would I put on this branch here? The snow has happened. What's the probability of a delay? I put 0.45 here, okay? So note that this number right here, probability of delay given snow, goes right there, okay? So then what number goes down here? No delay. 0.55, okay? It has nothing to do with this one over here, okay? Because we're just dealing now in the world of snow, okay? This side down here on the bottom is not possible because it has now snowed. So now there's either going to be a delay or no delay, and so it's going to be 0.45 and 0.55. Again, the different branches have to add up to 1. Okay, so what numbers do I put here and here? On the top I would put 0.1, and on the bottom I would put 0.9. Is that okay with everyone? Okay, so now I'm going to just go ahead and do my multiplication. I do 0.3 times 0.45, and I get 0.135, and here I get 0.165, and I get 0.07 and 0.63. Okay. This 0.135 is equal to the probability of snow and delay. Okay, so or also equivalently, you can, the order of the words inside in and does not matter, or doesn't matter. So we can say delay and snow. So these two are saying the same thing, okay? Probability of snow and delay is 0.135, probability of delay and snow, same thing, also 0.135, okay? Notice there is a great distinction between delay vertical bar snow and delay and using the word and here. Is that okay? All right, and so this would over here would be, you know, probability of snow and no delay. And I don't feel like writing all of these out, but I think you guys get the idea. Okay, but we're asking, what is the probability that the flight is delayed? So what numbers do I add up to get this number?
0.135 and 0.07.
Yeah, I would add this number. Okay, so this is, there was snow and it got delayed. But then there's also a chance that it gets delayed even when there's no snow, right? So I would add these two numbers. So what is the probability that the flight gets delayed? This is equal to 0.135 plus 0.07, and I get the answer of 0.205. And I could write it this way. I could write the probability of a delay is equal to the probability of there being a delay because of delay and snow plus the probability of a delay and no snow. Okay? Here we don't really care about the weather. We just want to know, were we delayed or not? And that's this answer. I'm sorry?
How did you get 205?
Did I add that wrong? 0.135 plus 0.07. 0.205. So there's two ways to get a delay. There could be a snow and the flight is delayed, and the probability of that happening is 0.135. There could also be no snow, but your flight gets delayed anyway, and the probability of that happening is 0.07. And so we add those two together and we get 0.205. Okay, is that okay? Let me copy this. And let's let me just change the question here a little bit. What if the question now is, you're picking your friend up from the airport and you notice the flight was delayed. The flight has been delayed. What is the probability that there was snow? Okay, so you're now at the airport, you look at the thing and you say, oh, the flight has been delayed. And so now we want to know, what is the probability that there was snow? How can we answer that? Okay. Well, how can I write this as an equation? So the probability here, we're asking, what is the probability that there was snow if we know that the flight was delayed? Okay. What is the probability that there was snow, there was snow, if we know the flight was delayed? Okay, well, we would write this as the probability of snow given a delay, okay? So notice that this is different from this. So where the words or the events are in relation to each other in the vertical bar, standing for given, changes. Okay, this says if there's snow, then the probability that there was a delay is 0.45. Now we're saying if there was a delay, the probability that there was snow is this number. Okay, so to get this, we're limiting ourselves to just the world where there has been a delay. Okay? Once we know that there's a delay, this no delay situation is impossible and this other no delay situation is impossible. Okay? So we're limiting ourselves to just the world of delays, and we want to know, of that world, what's the probability that we went down the path with the snow? Okay? So the answer to that is going to be 0.135, which is the path with the snow, divided by the probability that we ended up in this world in the first place with the delay. So it's going to be 0.135 divided by 0.205. Probability of delay, if you remember, was 0.135 plus 0.07, which gave us 0.205. So I have this answer, 0.135 divided by 0.205, and I get 0.659. So that is my answer here. Does that make sense? I'll let you guys write that down. So now I'm going to put everything that we did here into like equation form, which you may or may not like, but well, I prefer the trees over the equations, but I guess the equations are also important, and some people like the equations more. Okay. Can I go to the next slide? Yes. Okay. So we have, let's say we have two events, A and B. Okay. So we would say the probability of A and B is equal to the probability of A times the probability of B given A. Okay, so you could just imagine in the tree diagram with the snow and the delay, when we put the number here, that was the probability of A, like probability of getting the snow, and then over here this was the probability of B given A. And so when you go down the path, you get the probability of A and B, right? So probability of A and B is probability of A times the probability of B given A, and the labels are just arbitrary. So I could just flip B and A around and it would be equally valid, and so we can also write probability of B times the probability of A given B. Then this picture doesn't work anymore, but again the labels are arbitrary, so we could just flip everything around. Yes, question?
So the way that you solved it was that you got 0.135. Why did you divide that by the total of snow and delay instead of it just already being 0.135? Because isn't that going to be the probability of snow and delay
Okay,
over
so
anything else?
Let me flip back to that slide. Okay. So this answer 0.135. Let me just try to distinguish what all of these answers are. Okay. So we have probability of delay given snow is equal to 0.45. That's right here. And then I have probability of delay and snow. That is 0.135. And then I have probability of snow given delay, which is different from both of these, and that is 0.659. So these are all, they're asking different things. Okay, so the answer 0.135 is not the answer to this question. Okay, the answer 0.135 is tomorrow, what is the probability that you experience a snowstorm and your flight is delayed? Okay, that's different from what this question is asking, which is, we know that the flight was delayed. What was the probability that there was snow? Okay, which is different further still from, if there's snow, what's the probability that there's a delay? I know there's a bunch going on here, but I don't know if that clears anything up.
I was just, I get it when you go back. Because it's just like, for me, I thought that the probability of snow and delay is out of, like that probability 0.135.
So maybe I'll try putting a few more equations up on the board, and that might help. I don't know. We'll see. Okay, and even if it doesn't, ask more questions. Okay, let me just see if this helps, and if it doesn't, keep asking questions. Okay, so the probability of A and B is defined as such. Okay, thus we can also just rearrange our terms, and so we get the probability of A given B is equal to the probability of A and B divided by the probability of B, okay? And also the probability of B given A is equal to the probability of A and B divided by the probability of A. Okay. So in the last problem, depending on how you label it, okay, I think we can say, we can call A snow and B equal to delay, okay? And the pieces of information that we had was we knew that probability of snow was equal to 0.3, and the probability of delay given snow was 0.45, and the probability of no delay, of delay given no snow is equal to 0.1. And the question that we wanted to go after was, what is the probability of snow given a delay? And so essentially, if we call A snow and B delay, the question that we're going for is, what is this? Okay? And so using what we have, this has turned into the probability of snow given delay is, what is the probability of snow and delay divided by the probability of a delay. Okay, all I'm doing is just applying this equation right here. All right, and then we're going to break this thing up using this one right here, and we get, well, the probability of snow and delay is the probability of snow times the probability of delay given snow. Okay, and that's how we get 0.135 on the top. Okay, and on the bottom, the probability of delay, we had to break this apart into two pieces. This was the probability of delay, delay and snow, plus the probability of delay and no snow. Okay, we had to break it up into these things, and so we get all of the other parts, which was, this was 0.135 and this was 0.07, and so we get 0.205. So we have 0.135 over 0.205 as well, this way, just working with the equations alone. Some of you feel more confused this way, and that is okay, and some of you like it this way, and that's also okay. We're essentially doing the exact same thing, just in two different ways. Okay? One is with the equations and one is with the tree. Use what's comfortable with you, for you. Okay? You're not required, well, I might say draw a tree, but if you don't like the tree, you can use the equations and whatnot. Okay? Okay, let's take a 10-minute break here, and we'll come back and finish out chapter 3.